This is something that actually came out of the comments on one of the previous videos we did about birefringence, and somebody wanted to know whether double rainbows were the same kind of effect. So I thought I'd talk about rainbows. So really, to explain this, I need to do an experiment. I need to show you what a rainbow actually is. So I have here the sun and a raindrop. Not to scale, I have to say. And so hopefully with these two fine tools, we should be able to demonstrate the physics of rainbows. I need to switch the lights out. Okay, so if you kind of come down to my level, okay, so if you work your way around towards the right, there's a kind of a little, you can see the little white dot that's sort of reflected off the back of our giant raindrop there.
I can see it.
And as you go around, you will see that it kind of moves towards the right, so it kind of comes towards you, and then at some point, suddenly it turns colours, so you'll see it go blue, green, red, and then disappear entirely. And the point is you're currently 42 degrees away from the direction that the light's shining in from when you're at that point.
That looks nice, hang on.
Okay, so what we've got is we've got the light coming in, and as you can see, as it passes through this surface, so it goes from one medium to another, the speed of light changes, which has this effect of changing the direction that the light's travelling in. But the amount by which it gets changed depends on the wavelength of the light. Blue light gets bent a little more than red light, so you can see that the blue light reaches the back of the drop at a slightly different point from the red light. And then when they get reflected back again, and again there's another bit of refraction when they come out the raindrop again. And you can see that basically the red light, at least in these extreme rays, ends up travelling at a slightly wider angle than the blue light. That's when as you were panning around, the last light you saw was the red light. So you see just normal reflection pretty much all the way around to here, and then when you're at this last point, where it's the last angle that stuff can actually get through the drop at all, you first see blue light, then you see red light, then you see nothing further out at all. Of course, that's not what happens with a rainbow. With a rainbow, what you have, I'll show you another picture, is of course you have lots and lots of drops, which means there's always one at the right, exactly the right angle to send the red light towards you or to send the blue light towards you. And so actually what you end up seeing is that kind of, remember this magic angle of around 42 degrees. Anything that's around 42 degrees, this angle here between the direction the sun's rays are coming from and the direction you're looking from, you'll end up seeing either red light, or a little bit further out you'll see blue light. That actually means that rainbows actually are round, right? There's a circle of points that are 42 degrees away from this line to the sun. But what actually happens is that half of that circle is typically below the horizon, so that you see like half a circle of the light, and so you'll end up just seeing the classic kind of rainbow semicircle.
If you have to be at this magic 42-degree angle, how come I can see a rainbow and Johnny Smith 5 miles away can see a rainbow?
Because he's looking at a different set of raindrops. So he's still looking 42 degrees away from the sun, but from where he's standing, he sees a completely different set of raindrops that are all doing exactly the same thing back towards you.
So when I see a rainbow at my house and you see a rainbow over at your house, we're actually seeing two different rainbows.
You're seeing a different set of raindrops that are causing the effect. I mean, obviously it's the same sun that's causing the effect, and it's the same physics, but it's a different set of raindrops reflecting it all back to you. And the other thing you noticed is that when you went beyond, so when you were looking kind of closer to the sun, or sort of closer to straight backwards and forwards, so kind of when you're looking at light just reflected off the back of the raindrop, you saw basically white light. And it's only when you get to these extreme angles that you actually see the red and the blue light. And of course that's why if you look at a picture of a rainbow, you'll always see that inside the rainbow is always brighter than outside the rainbow, because inside the rainbow you're seeing just mostly that whitish light being reflected back. It's the sum of all the different colours being reflected back to you, so you see it as white light. Then you reach this edge of it where you're just about seeing just those last few colours, and then when you go to wider angles still, you see nothing at all, and that's why the outside of the rainbow appears darker than the inside of the rainbow.
At the start, I thought you were holding out the promise of something about double rainbows.
Double rainbows we can do too. So double rainbows, also again classically understood, going back at least to as far as, so Descartes did this experiment again in the 17th century. Lots of people have had a go at this. And what they realised is, so if we go back to our original picture for just a second, so what was happening here is the light comes in, gets refracted once off the back of the raindrop, comes back out, refracted again. In a double rainbow, what happens is the light takes a slightly different path. Another picture, you can have the light coming in, gets refracted, gets reflected once, reflected twice, and then comes back out again and comes out at a different angle from if it had just undergone a single reflection at the back. This is another way of making a rainbow at a different angle. So the first way still works. You can have the light coming in and getting reflected once, and that'll give us a rainbow at one angle, or it can go in, get reflected twice, and then we end up with a rainbow at two angles. So you end up with a picture like this. So we've still got the first rainbow here where the light's coming in, getting reflected back to us just once off the back of the raindrop. and so we see the colours spread blue to red. But there's a second way that it can happen, that it can actually bounce twice around the raindrop and take this rather more complicated path. And what you can see is that actually the rainbow ends up being reversed because of that second reflection, where the red light was originally on the outside. If you look at a second rainbow, you'll see that actually the colour is inverted, that the original rainbow, the inner rainbow, goes from blue to red, the second rainbow goes from red to blue. And in fact, all the effects are reversed. So as we were talking about before, you see a brighter light down here, then you see a normal rainbow. For the other rainbow, everything's reversed. So you see the second rainbow, and then you see brighter light further away. And so famously, you see this thing called Alexander's band, which is the dark region in between, where there's no white light gets reflected at all, because in the first rainbow it's all ending up down here, and from the second rainbow it's all ending up there.
It seems to me we should see a double rainbow every time, and yet we only occasionally see a double rainbow.
It really is because so what happens is that in the raindrop, most of the light just goes straight through, only a little bit of it gets reflected. And so actually it's a very inefficient process. Most of the light just travels straight through the raindrop, a little bit of it gets reflected. Of course, if you want to reflect it twice, that means a little bit gets reflected, and then only a little bit of the little bit gets reflected. And so the second rainbow is always much fainter than the first. So it is actually always there, and in fact, very occasionally you can even see a third rainbow, which is even fainter still. So these other rainbows are always still there, but they're always much fainter. So if you can only just see the primary rainbow, you're not going to see the secondary rainbow at all. And it's always when you have a really stonkingly bright primary rainbow that you end up seeing the secondary one. People often ask this question, don't you lose the magic of something by actually understanding it? By actually understanding where a rainbow comes from, isn't it not beautiful anymore because suddenly you've explained it and it's all very simple and trivial? And of course it doesn't, right? I mean, I understand the physics of rainbows, but I can still go out and look at one and say, wow, that's pretty. So it really doesn't have that negative effect at all. It just adds to the experience of seeing a rainbow. That not only does it look beautiful, but you actually understand why it looks beautiful too.